Have you ever wondered how the universe in all its vastness came into being? Our journey begins with a monumental explosion of energy and matter known as the Big Bang. But the universe we see today, with its galaxies, stars and cosmic structures, didn't simply spring into existence fully formed. Oh no, it all began in a state of extreme heat and density a fraction of a second after the Big Bang. Enter cosmic inflation, a theory that has revolutionized our understanding of the early universe. Picture this: in less than a blink of an eye, faster than you can say supercalifragilisticexpialidocious, the universe underwent a period of hyperfast exponential expansion. This isn't your average growth spurt. We're talking about a mind-boggling increase in size by a factor of about 10 to the power of 26. That's a 1 followed by 26 zeros. Now you might be asking, why should we believe in this fantastical idea of cosmic inflation? Well, without it, we have a hard time explaining why the universe appears so uniform on a large scale. You see, in those first fiery moments after the Big Bang, the universe was anything but smooth and uniform. It was a hot, dense soup of particles with temperatures and densities varying from place to place. But if we inject a period of cosmic inflation into the mix, everything changes. This superfast expansion would have stretched and smoothed out these irregularities like smoothing out the wrinkles on a crumpled piece of paper. The result? A universe that, on large scales, looks pretty much the same no matter where we look. This period of cosmic inflation, however brief, would have profound implications for the universe as we know it. It set the stage for the creation of galaxies, stars, and all the cosmic structures we see today. It's a concept that's as mind-bending as it is fascinating, a testament to the incredible power of the universe and the science that helps us understand it. So what could possibly cause the universe to expand at such a staggering rate? The answer lies in a hypothetical concept known as the inflaton, a scalar field that is believed to have driven the rapid expansion of the universe during the inflationary epoch. This inflaton is not like anything we encounter in our everyday lives. It's a field that permeates all of space, and its unique properties make the fantastic phenomenon of cosmic inflation possible. Now you might be wondering, how does a field cause the universe to inflate? Well, the inflaton is associated with a particular kind of energy known as potential energy. This is the energy that an object possesses due to its position relative to other objects, like a ball at the top of a hill. For the inflaton, this potential energy was incredibly high, and it's this energy that is thought to have driven the rapid exponential expansion of the universe. But it doesn't stop there. As the universe expanded, the inflaton field began to change, slowly settling into its lowest energy state, much like a ball rolling down a hill. And just as a rolling ball eventually comes to a stop at the bottom of the hill, the inflaton field also came to rest. However, unlike our ball, the inflaton field didn't just stop. Instead, it underwent a process called reheating, where the energy associated with the inflaton field was released into the universe. This released energy had astonishing effects. It heated the universe to incredibly high temperatures and created the particles that make up the matter we see today. But perhaps most significantly, it caused the universe to continue expanding, but at a much slower, more steady rate. What's remarkable is that this process happened in the blink of an eye, in less than a trillionth of a second. But in that brief moment, the universe went from a tiny, dense and hot speck to an ever-expanding cosmos, setting the stage for the formation of galaxies, stars and planets. As the inflaton field settled, it released energy into the universe, causing it to expand at an exponential rate. How do we know that cosmic inflation actually happened? It may seem like a question straight out of a cosmic detective story, and in many ways it is. Our primary piece of evidence, the cosmic microwave background radiation, or CMB for short. To understand the significance of the CMB, picture the universe shortly after the Big Bang. It was incredibly hot and dense, filled with a plasma of charged particles. Now, as the universe expanded and cooled, there came a point, about 380,000 years after the Big Bang, when these charged particles combined to form neutral atoms. This event, known as recombination, allowed photons or light particles to travel freely through the universe for the first time. These photons over time cooled down and now exist as microwave radiation. This is the CMB, a snapshot of the universe at a very early age. But here's the intriguing part. The CMB has an almost uniform temperature across the sky, about 2.7 degrees above absolute zero, with only tiny fluctuations. These fluctuations are the fingerprints of the early universe, tiny quantum fluctuations stretched to cosmic scales during inflation. The theory of cosmic inflation predicts these temperature fluctuations, and lo and behold, that's exactly what we observe. Satellite missions like the Cosmic Microwave Background Explorer, or COBE, and the Planck satellite have measured these fluctuations with extraordinary precision, further validating the theory of cosmic inflation. So, when we gaze at the cosmic microwave background, we're not just looking at a wall of microwave radiation, we're looking at the echoes of the Big Bang, the imprints of cosmic inflation, and the seeds of galaxies and cosmic structures. It's like reading the diary of the universe, penned in the language of light and gravity. The CMB, a remnant of the Big Bang, serves as one of the most compelling pieces of evidence in favor of cosmic inflation. So, next time you look up at the night sky, remember, you're not just stargazing, you're time-traveling, peering into the very origins of the universe. The theory of cosmic inflation doesn't just explain the universe's rapid expansion, it also solves some of its greatest mysteries. Consider the horizon problem. In the standard Big Bang model, distant regions of the universe had no chance to interact due to the finite speed of light. Yet our universe appears remarkably homogeneous, suggesting that these far-flung regions were once in close contact. Cosmic inflation proposes an elegant solution. In the blink of the cosmic eye, these regions rapidly expanded from a tiny, causally connected region to the vast universe we observe today, allowing for thermal equilibrium and the uniformity we see. Now let's think about the absence of magnetic monopoles, hypothetical particles with just one magnetic pole. Theories of the early universe predicted their existence, but none have been detected yet. Cosmic inflation comes to the rescue again, suggesting that these particles were so diluted by the universe's rapid expansion that their density became essentially undetectable. But cosmic inflation doesn't stop there. It also provides an explanation for the large-scale structure of the universe. The minute quantum fluctuations that existed during inflation were stretched to cosmic scales as the universe rapidly expanded. These fluctuations served as the seeds for the formation of galaxies, clusters of galaxies, and cosmic filaments, creating the cosmic web we see today. In essence, cosmic inflation takes these perplexing mysteries and weaves them into a coherent narrative about our universe's birth and evolution. It doesn't just tell us how the universe expanded, but why it looks the way it does today and how it got to be this way. It's a story of incredible growth, of tiny quantum seeds blossoming into galaxies, and of a universe coming of age. Cosmic inflation, therefore, provides a comprehensive framework for understanding the early universe and its subsequent evolution. Despite its explanatory power, cosmic inflation is not without its challenges. Critics argue that inflation is not actually predicted by particle physics and that it requires finely tuned initial conditions, making it seem less natural. Moreover, the inflaton field, the driving force behind cosmic inflation, remains purely hypothetical with no direct evidence to support its existence. This has led some scientists to explore alternative theories that could explain the universe's early rapid expansion. One such alternative is the concept of eternal inflation. This proposition suggests that inflation never truly ends but continues indefinitely, creating a multitude of separate bubble universes within a larger multiverse. Each bubble universe could potentially have different physical laws and properties, broadening our understanding of reality. While these alternatives challenge the traditional view of cosmic inflation, they also stimulate further scientific inquiry and discussion. The quest to fully understand the origin and evolution of the universe is far from over. The theory of cosmic inflation has truly revolutionized our understanding of the universe. This captivating concept suggests that shortly after the fiery birth of the universe, a period of stupendous growth occurred. A hypothetical scalar field, the inflaton, is thought to be the driving force behind this rapid expansion, setting the stage for the universe we know today. Cosmic inflation aligns remarkably well with our observations of the cosmic microwave background radiation, providing strong support for the theory. It also offers a compelling explanation for the large-scale structure of the universe, turning tiny quantum fluctuations into cosmic seeds for galaxies and clusters. Moreover, inflation neatly resolves the horizon problem, suggesting all regions of the universe were once in proximity, and explains the absence of magnetic monopoles. Despite challenges and alternative theories, cosmic inflation remains a cornerstone of modern cosmology. It's truly awe-inspiring to consider that the universe as we know it began with such an explosive and rapid period of expansion.